Hi. Good morning and welcome to our one of our REU talks on this one is going to be a smart and flexible microgrid with dynamic boundary by Dr. Lin Zhu, research assistant professor here at UTK. Lin Zhu is the research assistant professor in the Department of Electrical Engineering and Computer Science here at UT. He received his bachelor's and PhD degrees in electrical engineering from I'm going to say it wrong, so please correct me, Lynn. Hwasong University, I said it wrong. University of Science and Technology in 2005 and 2011, respectively. His current research activities focus on large-scale power system dynamics, smart distribution grid, and microgrid ESPI or co-PI of 8 projects sponsored by NSF and industry. So thank you so much for being willing to share your research with us today. And I'm going to mute myself and take it away.
Okay. Can you hear me and also see my screen?
Yes.
Okay. Okay, great. So today I'm going to, thanks for introduction and good morning or good afternoon, everyone. Today I'm going to talk about microgrid. And this project was supported by Advanced Research Project Agency, Energy, REU, under the award here. And also the project made use of the current center facilities. So thanks for their support. And here is the outline of my talk today. So first of all, I'm trying to give a brief introduction of microgrid and also their basic idea and concept. And after that, I will introduce the concept of microgrid with dynamic boundary. Usually the microgrid with traditional microgrid have a fixed and a clear defined boundary. But here, our concept here is a flexible, multiple dynamic boundary. And also we will introduce the design, development, and testing of microgrid with dynamic boundary using a real example. And also I will show a few video demos regarding our testing and experiment. So let's start. As we know, in a conventional microgrid, in a conventional power grid, utilities would be the only source which should deliver power to their customer. For example, the power, let me use my pointer. Okay, so you can see the power are generated in the power plant, either hydro, thermal, or even renewable power plant, and go through the transformer and go through the high voltage transmission and low transmission and go to your home, right? But if there's something wrong happened to the main grid, for example, the hurricane, tornado, and typhoon, and in that case, you lose your power. But if you have a microgrid, I mean, for example, the backup generator, solar PV, wind farm, and also the battery energy storage system, very close to your home or residential load, then you can keep your lights on. I think that is a major purpose of the microgrid. And what is microgrid? Microgrid usually consists of your customer load, like your residential, the building, for example, the UTK, the Minko building, that would be your load. And also you have different resources, even renewables, like backup generator, the battery energy storage, wind, solar, and even electrical vehicles, battery-based electrical vehicles. And they can play a role as a whole entity connected to the main grid. As you can see, this is a switch for illustration purpose. If the switch is on, the microgrid can be connected to the main grid. Then when you connect it, you can transport the power to main grid to serve the neighborhood, or you can receive or get the power from main grid to serve the inside the load. And so this is quite flexible. The microgrid can be connected or disconnected from the main grid. And regarding the operation mode of the microgrid, it can be like for the steady state. If it is connected to the grid, it's called a grid connected mode. If it is disconnected from the main grid, we call this islanded mode. It's autonomous islanded mode. And also between the two steady state mode, we do have a different transitions. For example, from the islanded mode to grid connected mode, we need to do the reconnection. Before we do reconnection, we need to make sure the voltage waveform, for example, including the voltage magnitude, voltage angle, and also the frequency of the both sides, they can match to each other. Otherwise, you will introduce a large inrush current. So this is a reconnection. Also, if you go from the grid connected mode to islanded mode, you can go through either planned islanding, that means everything is on the schedule, you have a plan, or because of fault, there are no plan. It's suddenly just disconnected from the main grid. We call it unplanned islanding. This is another transition. The last transition is black start. So you start from every beginning from black. So from the operating mode, we have two steady state mode and another 4 type of the transition. And for the microgrid type or definition, usually this is the definition from DOE, Department of Energy. Based on the service area or coverage area, we can divide the microgrid into 4 different kinds or categories. If the microgrid only serve, let me use a pointer. If the microgrid only serve a single customer, we call it the single customer microgrid. For example, you have a rooftop solar, you have small like electric vehicle, that would be your single customer microgrid, serve your single home. And if the microgrid is large enough, is able to serve the partial feeder. Feeder is just like a distribution line, usually like 12 kV, 12 kV. This is a feeder. It's able to cover or serve a load in a partial feeder. We call it partial feeder microgrid. If it's able to serve the entire feeder, we call it the full feeder microgrid. And if it's a larger service area, is able to cover the full substation, we call it full substation microgrid. So this would be the basic idea or definition of microgrid. So next topic would be the concept of microgrid with dynamic boundary. Previously, I mentioned that usually the microgrid has a fixed, clearly defined and fixed boundary, and you have a clear definition. There's a boundary. The one side of the boundary would be the main grid side, and the other side of the boundary would be the microgrid side. But here we want to propose a new concept with dynamic boundary. And we have a real example, and this microgrid already deployed at the EPP Chattanooga, which is very close to the Chattanooga city airport. So you can see this is the purple line here shows the coverage of one feeder. And the microgrid is located at the end of the feeder and along the runway of the airport. And along the runway, there is an airport solar farm, and the microgrid is installed here. And the right snapshot here shows the single line diagram of this feeder. So you can see the red dots here shows the substation and also the closed recloser or smart switches. And the airport solar farm and the microgrid is located at the end of the feeder. And the green dot here shows a normally open switch, because if the main grid, I mean this feeder is not available, we can reconnect it to adjacent feeder by closing those green dot switches. And yeah, let's show you a better signal line diagram here. This microgrid, we have 2.1 megawatt solar PV, and recently we added 2 battery energy storage system. Totally, we have 560 kW and 510 kW hour battery energy storage. And also we have 300 kVA grounding transformer. This is because when the microgrid running in the islanded mode, we want the system is fully grounded to reduce the overcurrent issue. And also we have 5 different load sections. You can see the load section 1, 2, 3, and 5. And S0101, this is the smart switches. And the load section are divided by the smart switches. Again, the microgrid is normally connected to the feeder number 1. And if feeder number 1 not available, we can reconnect to feeder number 2, number 3, number 4, or even number 5 based on the availability. So you can see we have multiple grid interface. The microgrid has multiple grid interface and a flexible boundary. Let me show you a better definition or illustration of dynamic boundary. Let's say, show an example. If the grid outage, if there is a grid outage because of extreme weather, for example, the hurricane or tornado, the microgrid will running in the islanded mode. So you can see none of the feeder are available. So microgrid running in the islanded mode or autonomous mode. Microgrid will be the only source inside the small microgrid. And if we have high solar PV generation, for example, during the noon or during the summer, during the day, we have enough PV, then we can cover all the 5 load sections. So the boundary would be here. The boundary switch would be S0101. In the contrast, if we don't have enough power, I mean, we don't have enough solar PV, like during the night, the battery, the storage can only support the critical load, like load section number 4 and load section number 5. So we have smaller service area. So based on the available solar generation, the boundary or coverage of the microgrid can be large or could be small. So this is the basic concept of the dynamic boundary. And next, I will introduce how we design and implement and deployment the concepts, this microgrid and this controller with dynamic boundary. And basically, we have 3 major tasks. So microgrid design, microcontroller development, and the testing and the deployment. For the microgrid design, we want to decide what would be the ideals on the optimal size of the battery to make sure the reliability of the critical load. And also we want to design where would be the best location for the smart switches and how we design the control system, how we design the communication system to support the control. Also, for the microcontroller, we need to consider what functions are needed and how we design the function blocks and how we implement the controller on the hardware platform. And after that, we need to test the controller. We have rigorous the testing. We have a testing procedure, step by step, from the pure simulation testing to hardware in loop testing and to the field testing. From everything is virtual to everything is real. And we have a strong team. As you know, UTK is the lead, and we have National Instrument. They provide this is our vendor. They provide the hardware to implement the controller. And EPRI is our Electrical Power Research Institute, is our consultant. They provide their comments, suggestions, and advice to guide us. And EPB and the TVA are utilities. They are our potential customer. Their microgrid is deployed as EPB microgrid, their feeder, electrical power board. This is the distribution utility, and the TVA would be the regional transmission utility. So we want to look at the function of the microgrid on both sides, either smaller distribution grid and the transmission level. And also GEC, Green Energy Corp, would be our technology to market. Later on, we want to bring their technology to the market eventually. So we do have a strong team and with closer collaboration. And for the microgrid design, we designed 2.1 megawatts solar PV is not enough. We add another 600 kW, something kW solar PV. You can see here. This is the runway along the airport. So as you can see here, this is the phase 1, 2.1 megawatts solar PV. And right now we added another 600 kW solar PV. And the battery, 560 kWp battery are installed here, still along the runway. And also we have the battery controller installed just aside the installed battery to do the control purpose. And regarding the control, regarding the microgrid design, the purpose to design the microgrid control system regarding the siting and the sizing of the PV battery, and also we developed the design guideline, which is a general procedure for siting and sizing of microgrid assets for use as EPB and other utilities. For the design purpose, for example, our targets have 4 purposes here or objectives here. For example, the energy efficiency improvement, our target 20%, and based on paper design, we can reach 35%. And the emission reduction, like we reduce the greenhouse gas emission from 20, the design target is 20%, but we can reach like 34%. And the average interruption time on the extreme weather, like a hurricane, our target is 15 minutes. And without the microgrid, the number would be 300 something minutes, quite long. But with the microgrid, we have another additional source because of microgrid. The number can be reduced to 15 minutes. And also the reliability of the critical load can be reduced to 1 minute. Previously, without the microgrid, it's roughly 50 or 49 minutes. So this is our design to decide the size or siting of the microgrid assets. And also the second major task is controller development and implementation. Here the controller development comply with the standard IEEE 2030.7. That's one specifies the microcontrol function, which includes the basic monitoring function and the dispatch. I mean, during the steady state mode, like either grid connected mode or islanded mode, we can do the monitoring, we can do the forecasting, we can do the energy management. For example, we can determine when we need to charge the battery and when we need to discharge the battery. For example, like the load reduction or peak load reduction. And also the control function need to facilitate the transition between the 2 modes. For example, the reconnection, planned landing, and unplanned landing, and the black start. And also the all the control functions are implemented on a general purpose hardware platform. As we can see here, this is the general platform provided by NI, our vendor, National Instrument. After that, the controller is implemented. We do different type of testing. So at the very beginning, we developed the algorithm, and we do the testing in MATLAB Simulink. So you can see everything is virtual, everything is software. The microgrid circuit model are virtual, and also the controller are virtual. Then we move to the reality step by step. So step 1 is the controller hardware in loop testing. That's to say the grid or microgrid asset and communication. The grid assets are emulated on the hardware, I mean the real-time simulator, but the controller is the real thing, emulated outside the real-time simulator. So we can do, in this way, we can do the controller hardware in the loop testing to verify the controller performance. And the step 2 is the hardware test platform. Previously, the microgrid assets like a PV battery, they are still virtual. But when we move to the hardware testbed at UTK, the PV and the battery and the circuits would be the semi-physical system. Although it's not a real one, but it's still close to a physical system. The power electronics devices are emulated by the low voltage converters. So this would be the semi-physical physical system. And also we included the real measurement and the communications. The last step is the field test. You can see the battery, PV battery are real thing, and also the controller, communication, everything is real. So, but in this way, by this step-by-step testing, we can step-by-step verify and test our controller and make sure the controller can perform well as we designed and expected. Okay, so let me basically quickly introduce the controller testing on all-party HRL test platform. So you can see the real-time simulator is able to emulate the microgrid circuit, the PV, battery energy storage, and the smart switch, we call it interrupter. So the primary side, I mean the microgrid assets are included in the real-time simulator. Also, we have desktop PC. This is used to set up the system model and for visualization. And we have the controller. Here we have one battery load controller and one PV load controller. And also we have a centralized controller at the higher level. The communication protocol we use DMP3, which is very popular in distribution level. And also here is for field testing, we already integrated the system, the controller into the real system. For example, we deploy our local controller to control the battery and the central controller to control the entire system. Also, this is a hierarchical control structure. So we have a local level controller, device level controller as in the field, and also the local controller also at the local level, and the central controller as the control center. And you can see also they are connected or integrated to the existing DMS SCADA system. For example, to get the smart switches information and also to get the status of the PV, we utilize the existing communication assets. We don't need to build or add an additional asset to build the controller, microcontroller. So the purpose is to fully utilize the existing smart grid assets, including monitoring, sensor, and communication assets. So they are already in place, and right now we are conducting our field testing. So next I will show you a few demos here, including the demo on the all-party testing and also HTTP testing. So let me introduce the configuration or HIM on the HMI or for visualization. So this is a reduced circuit model based on the realistic feeder SEPP, the utility. And we have three, let me use my pen. Okay, so in this reduced model, we have three grid interfaces like a G1 on the left and G6 on the top and G14 on the right. And the red line here means the circuits distribution line, and the L5, L2 start with L. Those are load sections. And the red dot and the green dot means the interrupter, I mean smart switches. And you can see the red here, red dot means the closed switch. And the green dot means the open switch. And we have two assets here, the aggregated, the PV, roughly 2.1 kilowatts, and 500 something battery. And to control this microgrid, we have one central controller and two load controller, PV load controller and a battery load controller. And the load controller, we have different functions, and you can see if they are highlighted, that means the controller is, control function is enabled. And also in the central controller, we have like a state estimation, communication, black start, and load forecasting, PV forecasting, all kinds of different function blocks. And based on different microgrid states, the function can be enabled or disabled automatically. So you can see this is a microgrid state indicator. Right now is a grid connected mode. And also we have different control panel here. So let me show you a quick video demo. First, the video I want to show is the protection. So we have 3 different fault locations, like fault location 1, fault location 2, and fault location 3. So let's start. I think at the beginning we tried the fault location here, and this is the temporary fault. And you can see prior to the fault, the system running in the grid connected mode. The microgrid can connect it to the grid interface G1. And if we apply a fault at the low fault location 1, and both sides will trip, we isolate the fault. I mean the grid side and the microgrid side. And you can see the fault is totally isolated by tripping the smart switches on both sides. And because this is the temporary fault, the system will be recovered soon. Yeah, let's continue. Okay, yeah, you can see the main grid side will recode first, and then we come to the boundary switch. And then we need to do the synchronization to make sure the voltage waveform, frequency, angle, and magnitude can match to each other. Then we can close this switch. So right now, the controller is doing the resynchronization. So you can see the angle difference between the both sides is reducing like a -8. Then it's within the threshold, we are closed successfully. And you can see the microgrid is come back to the grid connection mode. Next, we try another fault. Yeah, in this case, this would be a permanent fault at the same location. Again, both sides will trip to isolate the fault. And under this in this circumstance, because this is a permanent fault, the grid side will try to recode 3 times, and after 3 times, all of them are failed. Then it will block this one. And you can see in this condition, the microgrid will already come to the islanded mode. It's disconnected from the main grid. Right now, this switch is trying to recode 3 times, but it's failed. Okay, then you can see because it's blocked, lockout, and then if we, at the very beginning, we do have enough solar PV here, it's able to cover all the load section all the way down to here, to load L8. If we don't have enough PV, so you can see right now only 3.1 kilowatts, the microgrid will shrink its boundary to serve the critical load. Yeah, you can see that will happen. Yeah, it's will share the load section L8 and L7, probably further share the load section L9. Okay, sorry. Okay, so in this case, if we don't have enough PV, only load section L9 and L8 will be served. If we have enough PV, the microgrid will expand its boundary to pick up a load to expand the boundary of the microgrid. Yeah, you can see it will pick up the load all the way down to L3 and L2. So it's quite flexible. The boundary will be, it's a flexible boundary based on how many PV and renewables you are available inside the microgrid. Okay, next I think we will apply another fault at the load the fault location L3. It's still islanded mode, and because we don't have, because there's a fault here, the microgrid will shrink the boundary and also curtail the PV output to maintain the active power balance within the smaller area. So you can see the PV, the number is reducing. And again, this is a temporary fault. The microgrid the fault can be recovered. So if we are restored all the load section way back to load section L2. If this is a permanent fault, yeah, again, the fault will be isolated on one side only, and we will do the PV curtailment to reduce the PV output. And also we will switch the mode of the battery from the discharge mode to charge mode. So to fully utilize the PV resources and make sure the system, the active power and reactive power inside this small area is balanced. So it's a quick summary. The microgrid is with flexible boundary. In this way, we are able to fully utilize the renewable resources. This is demo number 1. And demo number 2, what I'm showing is another case. Let me show you the reconnection. Yeah, again, prior to the fault or the disturbance, the system is connected in the grid 6. It's in the grid connected mode. And here we can do the planned islanding. Yeah, let's see. We will disconnect from the main grid. Oh, sorry, it's unplanned islanding. We disconnect from grid G6. You can see this one is open. And because we don't have enough the source to support all the load section, the controller decide we share the load section L11 and also the load section L2. Yeah, further share the load section L5 and L4. Yeah, later on probably we can reconnect to the grid. Oh, sorry. Here if we further reduce the PV output, we can further reduce the shared load section. Yeah, if we increase the PV output, the boundary can be extended to pick up more load sections. And the next, we will reconnect to the main grid. And you can see, yeah, this one very quick. This happened, both sides of angle and the voltage are consistent to each other. So you can see the main grid is connected, and after that, everything will restore to the prior state. Okay, let me show you our testing on the hardware test platform. It's a bit noisy because we recorded the video live. You can see, let me introduce the diagram here. This is the hardware, the test platform. And this shows the top right shows the waveform, like a battery voltage and the grid side voltage. And the microgrid is a little bit different. We have PV as node number 9 and the battery as node number 10, and also battery as node number 12. We have 2 grid interface at G1 and G4. Prior to the testing, the grid is connected to the main grid at G1, and those block shows as the smart switches. And all others are like L11, L8, and L7. Those are the node sections. Okay. If we have temporary fault, this one will trip to isolate fault and recover it soon. It's doing recoding. You can see the click on the background. Yeah, it's recovered. Yeah, we try the permanent fault. Yeah, you can see the system in the islanded mode, and also boundary shrink because we don't have enough source. And the main grid side will try to recode 3 times. Yeah, you can see this is the first try. There's still the fault, and then it's temporary reclosing and disconnected. The second try, and after three attempts, the smart switch will be blocked. And if we have enough source, the boundary can be recovered, extend the boundary of microgrid. Inside the island microgrid, we can apply a fault. It will trip isolated fault and reclosing. After, if the reclosing is successful, it will pick up all the load section until this switch. Yeah, again, we try the permanent fault at load section 11. Open to isolate fault and then try 3 times. You can see if the trying is a yellow color, if it's a block, it will be gray. Okay, you can see it try 3 times. The first one is a fault, and the first try, second attempt, and the third attempt, it will be blocked and it will turn to gray. Next, we will do the reclosing. Yeah, we clear the fault and start resynchronization. You can see my grid is islanded mode. The grid side will pick up load section until here. This would be the boundary switch. And then the controller is doing the resynchronization. You can see the battery voltage and the grid voltage is in the same phase. Once their voltage magnitude, angle, and the frequency are close to each other, we can close this switch. Bring the microgrid to the islanded, from islanded to grid connected mode. Then we can pick up all the rest of those sections. Okay, I think that's all for the demo part. Last, I will give a quick summary. So what is microgrid? Microgrid is an additional asset to keep your lights on in case of main grid outage, for example, extreme weather conditions. Our team have developed a microgrid and its controller with dynamic boundaries. Also compared with the conventional microgrid with a fixed boundary, this new microgrid is smart and more flexible. And because it can require smaller battery energy storage, because you know the battery storage is quite expensive for now. And also with the flexible boundary, we are able to fully utilize the renewables. We have finished the testing on the OPRT HL test platform and the HTB hardware test bed at UTK. Right now, we are doing the field test, which is ongoing. And you can see we are trying to bring the technology to the market. And this is REU Energy Summit in 2018. And the team is trying to introduce the system and doing the live demo to our potential customer. And also we have the open source release to the as a GitHub. And this is a basic function on the component of the controller. The advanced component, we want to keep it as our potential, as our confidential. Yes, I think that's all I have prepared today. And any question or comments? Yeah, I'm happy to answer your question. Thanks.
I have one quick question.
Yeah, go ahead.
That I wasn't real sure of, and I don't have a good background. So when you were talking about the reliability of the critical load and that your goal was to keep it under a minute, does that mean that you wanted the system to be able to switch and take over in under a minute?
You mean this one?
Yes. What does that mean?
Okay, yeah, those are the two objects that are a little bit different. This one's the interruption time. That means, for example, you have extreme weather,
Right.
and the average for each customer, their interruption time is within less than 15 minutes.
Right.
And here we still use the same steady reliability indices to evaluate the reliability for critical load. This is within 1 minute. Again, that means you have interruption, but the interruption would be within 1 minute. Yeah, in average. Yeah.
Okay.
Yeah, it does not mean you don't have any interruption, but that means you will be recovered within 1 minute.
Within a minute.
Would that be considered a transient, and the rest of your modeling would be considered steady state?
On transition.
No, I said transient.
Okay.
And the rest of the function would be considered steady state?
Transient, I think you are,
When you're modeling this, you have steady state and then you have transients. Would this be considered, say, a prolonged spike?
Long spike. That would be not the transition. This is
Okay.
This is just a transient because you close down the switch. Yeah.
I've got a question. So as far as implementing this microgrid and these smart switches, how many, like, is it actually in use today yet, or is it still in development?
Okay. You are saying the microgrid asset or the controller or the whole system?
Sorry, I guess these smart switches, like the whole idea of that, like, is it implemented yet, or is it still in development?
Okay. Yeah, for EPBs, they are very advanced because they deploy like 1,200 smart switches, and other utilities based on our survey and based on our survey, I think there are some, most of the utilities, at least they have some smart switches in their certain circuit breakers, certain feeders. So actually there are lots of the smart switch, we call it recloser or other names. They have different names, but they are have the similar function. They are already deployed in today's feeders. Yeah.
That's cool. Okay.
I have a question. How many solar powered substations do you guys have now?
Okay, so yeah, good question. The full capacity of this feeder is 5 megawatts, and the total capacity of the battery and the PV together is roughly 3 megawatts. So we call it a partial feeder microgrid. Yeah.
Okay. What kind of batteries you're using in this thing?
I'm sorry, and you are saying the battery?
Yeah, what kind of batteries are you using? Are you using lead acid? Are you using lithium polymer? Are you using nickel iron? What kind of batteries?
Sorry, I could not remember what's the material we use for.
Okay.
Battery. Yeah, I think there is a NEC battery. I cannot remember. Yeah, I forgot that. Sorry.
Kind of off his question, but these must be giant batteries, right? Like how big?
Oh, you mean in kilowatts or the?
Well, I guess both, like physical size and power, right? I mean.
Okay, you can see this is the size in KW and kWh is 560 and 510 kilowatts and kilowatt hour respectively. And size, you can see here, this is NEC. This would be the two, I think those are two battery energy storage system, yeah.
Okay.
Let me give you a clue from our world. I think they'd have to have Avogadro's number of plates.
Just about.
Yeah.
I think it's quite small, yeah. And this would be the controller. Yeah.
I have a question about like the simulation kind of. Like when there's like a fault and the PV output was lower than usual, and like say like some loads like didn't have power going to it, like why didn't like some of the other grid inputs, why didn't like the system like close those switches so that the like that grid out input could serve that load.
Okay, I see your point. You are saying why we cannot pick up load on the adjacent feeder, right?
Yeah, like say for example, there was a fault and like the PV output was lower, so then it made the boundary like it made the boundary smaller, so that like say like load 4 and 5 didn't have any power to it.
Okay,
like
yeah.
Why didn't like G6 close?
Okay, I see your point. Yeah. The question. So someone probably need to mute. Okay. So yeah, I think this is a very good question. The reason is that, for example, this is another feeder, and this is another normally open switch to try to connect this feeder to another feeder. And you can see another feeder, they have their power and their supply all the way along to here. If you close this normally open switch, then you close to another source. You do need to go through the resynchronization to make sure that both sides voltage can match to each other. Otherwise, you will introduce a large inrush current and may damage the equipment.
Yeah.
For that reason, we cannot pick up load on the adjacent feeder. The only thing we can do is to change the mode of the battery and also curtail the solar PV. Yeah. Did I answer your question?
Yes, thank you.
Yeah.
Okay.
So what exactly does black start mean?
Okay, black start means everything is shut down. For example, you get the PV, for example, the sequence for black start is like this. We start up the battery in voltage mode to support the voltage and pick up the smallest load like L10. And then we bring the PV in, and then we pick up the one load section step by step to make sure, because every time you bring either load or the source, you introduce a disturbance to the system. We make sure the transients are gone, then we can pick up another section or pick up another source. So this is a step-by-step process. From everything is outage, everything is disconnected. From this the process we call black start.
Okay. So do you run the risk of damaging any equipment with the sudden onrush of all that current?
You are saying if they're in rush current, will damage the device? Or?
Yeah, is it possible? Have you guys thought about that?
We do have this is related to our design.
Okay.
Because we have the smart switches divide the load section with a smaller size, like each will have like a 200 kilowatts or 300 kilowatts.
Okay.
And so we pick up once we pick up the one load section, we can get the inrush current, but the inrush current is under control. And also when we pick up load section, we don't pick up the load section as a whole. We pick up one by one. For example, when we expand the boundary, we pick up this one and this one one by one to make sure the disturbance applied to the system is smaller enough and under control.
So you use your nodes to control that. That's cool.
Yeah, we do have the field test at EPP Chattanooga, and we already tested the unlanded operation, the grid connected operation, and we're trying to do the transition. Yeah, so we didn't see any problem or issues during the testing.
Wow.
So if no any other question, and probably I will get back to you.